Okay, the next thing we're going to talk about is the Taylor series, which is a special kind of series. It's a little bit like a power series, in a weird kind of flavor, but a power series of complex exponentials, which is something that's may probably be very unfamiliar to all of you. But the reason why that's the case is, one, because we love power series, two, because power series arise naturally out of Taylor series, and three, because there's something called the Euler relation that relates complex exponentials to sines and cosines. Sines and cosines are those lovely functions of ours that are periodic, so repeat themselves over and over. So what this allows us to do is to decompose, say, a time series or a set of measurements over a particular length scale into underlying sinusoidal signals with different frequencies. We can do it for signals of any resolution. There are actually techniques to do it even for irregular samples of any resolution. We can do it over infinite time series, we can do it over finite time series, all of those things in principle. In a little while we're going to get more down to brass tacks and think a little bit about how to do that with particular observed data sets or kinds of observed data sets. But for now we're just going to think about the series as a power series of the complex exponential type. I'll show you what that means. Great. Okay, so here's the Fourier series written two different ways. Written at the top is written as a complex exponential. So for the zeroth term we just have a constant. For the first term we have some constant, and then we have e to the ix. So x is our independent variable. E to the ix, this is the Euler constant. Why there's an I there, it's complex, we'll see in just a second. Plus, here's the next term, so we're going to go to e to the 2ix. So if this is the thing, e to the ix is the thing that's playing our role of the thing that we're raising to higher and higher powers. Now we're raising it to the second power. Here's the first power, here's the 0th power, here's the third power. Okay, I claim, we're going to see why in a second, this is exactly equivalent to a sum of two different infinite series. The first one, a0 with the 1/2, so that's our constant coefficient, that's the same as this one, plus a1 times the cosine of x, plus a2 times the cosine of 2 times x, plus a3 times the cosine of 3 times x. So for those of you who thought a little bit about cosines, this one goes from 0 to 2 pi, and this function goes from -1 to 1 and back again. That is the cosine. This is when 2x goes from 0 to 2 pi, so it goes through it twice as fast. This guy's a different frequency. It's basically a higher frequency than this term, double the frequency, triple the frequency, and so forth. Now we get on to here. There's also sines and more sines of higher and higher frequency. There's no constant term here because the way we've decided to split this up is that all of the things that are even, that means if I reverse the sign of x, I get the same answer. Just like an even power of x, like x squared is the same if x is negative or positive. X to the 4th is the same if x is negative or positive. X to the 6th, so on. X to the first power, of course, flips sign when you make x positive or negative. X cubed flips sign when you make x negative or positive. So we've collected together all of the even ones. Cosine is an even function because the cosine of x is the same as the cosine of minus x. A constant is the same because it doesn't depend on x at all. So if it's always the same value for positive x and negative x. And then sine is odd. It flips sign. That means that if x is plus something, then sine of x will have negative its value when x is evaluated at minus that same something. Same is true of sine 2x, sine 3x. So I've split into even and odd. But it's totally not at all obvious why these sines and cosines are supposed to be equal to this complex exponential. So, in the Taylor series video, we actually did the Taylor series for e to the x. Let's look at the Taylor series for sines and cosines as well, which will be derived in exactly the same way. I'll leave it to you to do it, to get term by term what the Taylor series expansion is for sine and cosine. Here's the one for e to x that we already figured out, 1 plus x over 2 factorial plus x over 3 factorial, and so on. Here's the one for sine. There's no 1, but there is an x, and then minus x cubed over 3 factorial. So look, there's a match to those two terms in the e to the x expansion. And now here's the one for cosine. There is a 1, and then there's x squared over 2 factorial, which is the same as this. So every term in the e to the x has a matching partner down here, almost matching partner, in the sines and cosines. Except for the fact that there are minuses in here that are not in here. And written in this form, you can see there's a minus 1 to the n power minus 1 to the n power in the cosine form and the sine form. It's just not there in the e to the x. So how do I get a minus 1 to the n power out of this? Well, how do I get a minus 1 up here? Well, I could use the special trick of the square root of minus 1, I, the imaginary beast. So if I put in an I in there, it is a negative, but if I square it, 2 powers of I times I, then I get a minus 1. So if I put in, instead of e to the x, e to the ix, then I would have, for the n equals 1 power, I would just have I times x. But for the n equals 2 power, I'd have minus x. And so, here we go. I claim that if you work that out carefully, it tells you that e to the ix is equal to cosine of x plus I sine x. Using this, we can show that these two are equivalent with the right kinds of choices of A0, A1, and now we're realizing complex coefficients, C0, C1, C2, in order to make this all work out. And the last little part of this story that I wanted to point out here is just to say, notice that there are both odd powers and even powers in the e to the x. Even, odd, and so on. In sine of x, which is an odd function itself, because sine of minus x is equal to minus sine of x, there are only odd powers in the expansion. X to the 1, x to the 3, both odd powers. Whereas in cosine of x, which is an even function, because cosine of minus x is equal to cosine of x, there are even powers. 0, 2. That's it. So we can express functions as combinations of sines and cosines. We kind of have a handle on what that means for different frequencies, but also as complex exponentials. And as we go on figuring out different ways to determine what all these coefficients are to match particular functions, that's going to be really useful. We'll be able to jump back and forth between the two modes, and it helps to keep track of all these minus signs to use the complex exponential form.